Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 12th physics, get more than 95% marks series, electromagnetic induction, chapter 6, ncert line by line, part 4. Before we start today's class, we have a humble request. Please subscribe our channel if you have not done yet. Please like and share our videos with your friends and relatives so that they can also get benefit of these videos. Please click on the bell icon so that you will not miss any of our videos, because you will get, on clicking on the bell icon, you will get automatic notification whenever a new video is uploaded. Let us start today's class. Energy consideration, a quantitative study, section 6.7. So in section 6.5, we discussed quantitatively the Lenz's law is consistent with the law of conservation of energy. Now we shall explore the aspect further with a concrete example. Let R be the resistance of a movable arm PQ of rectangular conductor shown in figure 6.10. We'll see the figure later. First, read what are there in the figure. We assume that the remaining arm QR, RS, SP have negligible resistance compared to R. Thus, the overall resistance of the loop is R and does not change with PQ is moving. As PQ is moving, the current I in the loop is I is equal to E upon R. Now let us see the figure. Then we can conceptualize that what is happening. So here is the figure, the same figure. Okay. So PQ have a resistance R, and other sides QR, RS and SP have negligible resistance with respect to PQ. So we can write I is equal to E by R. Why? Because I is equal to V by R, we can write. V is the potential difference, and V if there is a EMF, then we can write E by R. R is the resistance. Instead of E, we can write BLV, where B is the magnetic field, L is the length, and V is the velocity upon R. R is the resistance. So this we have already done in the previous sections. To go for more details how this equation is derived, please watch our previous videos, electromagnetic induction part 1, 2 and 3. On account of the presence of the magnetic field, there will be a force on arm PQ. The force will be force I L cross B is directed towards the direction opposite to the velocity of the rod. The magnitude of the force is I L L into B, I into L into B, and instead of I we can put this. So ultimately the equation turns as force is equal to I L B. and from equation 6.7 we got I is equal to BLV upon R. Here R is the resistance. So putting this value here, so F is equal to BL, instead of I we'll put BLV upon R into L into B. So ultimately we got B square F is equal to B square L square V upon R. Now till here it is cleared. You are with me, students? Any problem you can write in the comment box, where we use equation 6.7. So we have already used equation 6.7 and we came to this value. Note that this force arises due to the drift velocity of the charge responsible for the current along with the rod that consequent Lorentz force acting on them. Alternatively, the arm PQ is being pushed with a constant speed V. The power required to do this is P is equal to FV. P is equal to F into V. And instead of F, we can write this value instead of F. So instead of F, if we write this value, then B square L square V upon R multiplied by V. So ultimately we got B square L square V square upon R. F is equal to this value. Now, so F is equal, this is P, power. P is equal to this value. So one more question, power is equal to F into V. Remember, force into velocity. How come power is equal to force into velocity? In class 11th you have learned. So power is equal to work done upon time. Now work done we can write F Fs, force into displacement or force into distance. So F S upon T, which is equal to F S upon T is V. So power is equal to, we can write F into V. So we have written power is equal to F into V here. And instead of F, we have put this value, this entire value instead of F. And instead of V, nothing, just V is alone. So after that we multiply and we got power is equal to this much. Now, which is identical to equation 6.8. So let us see equation 6.8. Oh, we have left something. So the agent that does this work is mechanical. Where does this mechanical energy go? The answer is it dissipated as joules heat and is given by. So power is equal to here heating effect of current, that is joules heating effect, and power is equal to, in terms of heating effect, we can write I square R. So instead of I, we can write BLV. BLV is equal to what? So I square R in shortcut. So I is equal to I square R. So I is equal to, this is the EMF, BLV is the EMF. So I is equal to EMF upon R. V by R, that is EMF by R. So EMF is equal to how much? BLV, or R is equal to R. So we can write BLV by R from here, and whole square multiply by small r. So we can write B square L square V square upon R square multiply by R. This get cancelled. So ultimately we got B square L square V square upon R, which is same as that of this. So in both way we can find out the value of power. Thus, mechanical energy which was needed to move the arm PQ is converted into electrical energy, the induced EMF, and then thermal energy. This is an interesting relationship between the charge flow through the circuit and the charge in the magnetic flux. From Faraday's law, we have learned that the magnitude of induced EMF E is equal to delta phi B upon dt. However, delta modulus of E is equal to IR, that is Q delta Q by delta T R. Thus, delta Q is equal to delta phi B by R. So let us understand this. So first line, how this came. Modulus of induced EMF is equal to delta phi B by delta T. Why? By the definition. By the definition of the induced EMF, which we have learned from Faraday's law. Rate of change of magnetic flux. So rate change of magnetic flux is delta phi B. Rate is upon delta T. So rate of change of magnetic flux is delta phi B upon delta T. Again, we can write modulus E, modulus of E is equal to IR, that is I is equal to, we can write I. What we can write I? What is I? What is current? Rate of change of electron, moving electron. So charge, rate of change of charge. Instead of I we can write this, and instead of R it is R. So we can write delta Q by delta T R I is equal to, we can write this. So the same is written here. Same is written here. So I is equal to this much, and E is equal to IR. IR. So put the value of I, that is delta Q by delta T into R is equal to delta Q by delta T R. E is equal to this much, and same we have written here. So now if we equate this to equation, what we will get? If we equate this equation, so we'll get here, instead of E, instead of modulus E, can we write this here? Of course we can write. So this delta T is equal to delta Q delta T R. Now delta T gets cancelled. Now delta phi B. So delta Q into R is equal to delta phi B. So delta Q will be equal to delta phi B upon R, delta phi b upon R. So here we got this. So we got the value of charge, delta Q. Now we have one example. Refer to figure 6.12a. The arm PQ of the rectangular conductor is moving from x is equal to 0 outward. The uniform magnetic field perpendicular to the plane and extends from x is equal to 0 to x is equal to b and is 0 for x is greater than b. Only the arm PQ possesses substantial resistance R. Consider the situation when the arm PQ is pulled outward from x is equal to 0 to x is equal to 2b and then moved backward to x is equal to 0 with constant speed v. Obtain expression for the flux, the induced EMF, the force necessary to pull the arm and the power dissipated as Joule hit. Sketch the variation of quantities with distance. So let us go through the question again. Reference 6.12a. So this is the figure. The arm PQ of the rectangular conductor is moved from x is equal to 0. So this is the arm PQ. This one, this arm. And it is moving towards this direction where arrow is put and from x is equal to 0 outward. Outward means right side. If we look at this direction, arrow's direction. The uniform magnetic field perpendicular to the plane was extends from x is equal to 0 to x is equal to b, and it extends from x is equal to 0 to x is equal to b. So this is the magnetic field represented by dots, and this magnetic field extends from x is equal to 0 to x is equal to b. Fine. And is 0 for x is greater than b. So it becomes x is and the magnetic field becomes 0 when x is greater than b. Only the arm PQ possesses substantial resistance R, and the substantial resistance of PQ is R. Consider, and no other arm have resistance. Consider the situation when the arm PQ is pulled outward from x is equal to 0 to x is equal to 2b. So we have pulled the arm from x is equal to 0 to x is equal to b. 2b. 2b means till here. And then move back to x is equal to 0. And again what we have done, we have moved back to x is equal to 0. Fine. With constant speed v is constant. Obtained expressions for the flux, the induced EMF. So we have to find the expression for flux, we have to find the expression for induced EMF and the force necessary to pull the arm and the power dissipated as Joule hit. Sketch the variation of these quantities with distance. So how these quantities will vary with the distance? Because we are moving PQ, so the distance is increasing. So how it will vary with the distance, that you have to. Again we are pulling back, the distance is decreasing. The x distance is decreasing. So when we are pulling back to x equal to 0, so how it will react with the distance? Solution. Let us first consider the forward motion from x is equal to 0 to x is equal to b. So flux phi b linked to the circuit SPQR. So where is SPQR? SPQ and R, this circuit. Phi b is equal to blx. B is the magnetic field, x is the is the area of the rectangle, where x is greater than equal to 0 and less than b. B L B B. So instead of x, what we can write, b and x is greater than equal to b and less than 2b. So instead of x we can write b. So phi b is equal to blb. The induced EMF is E is equal to d phi by dt minus d phi by dt minus, uh, instead of phi what we can write, minus blv, where x is greater than equal to 0 and less than b, and which is equal to, which is for the value of x is greater than 0, greater than equal to 0 and less than b, we get EMF is equal to minus blv. But for the distance b, x is greater than equal to b and less than equal to or less than 2b, then we get 0, because b, capital B magnetic field uh, is greater for is 0 when for greater than b, x is greater than b. So when the induced EMF is non-zero, the current I is in the magnitude I is equal to blv upon r, E upon R. I is equal to E upon R, and the I is equal to EMF upon R. So E is equal to BLV upon R. Now different stages they have shown in the graph, how they came up. Let us discuss. So in x-axis we have put 0 to B, B2 to B, again 2B to B, and B to 0. This is the entire motion. So first 0 to B, what will be the power? So power is very simple. What we have written, power is equal to work done we upon time. So we have already uh, put the values of W, that is B square L square V square upon R. So putting these values, how come BLLV? We have already proved this in previous video how it came. So unnecessarily again we will repeat it. Please go through the video number 3. You'll find these expressions. So directly will come power is equal to this for this 0 to B. Again force will be minus B square L square V by R. Again, so for this reasons from 0 to B, for 0 to B, force EMF is equal to minus BLV. In this way we have found all the quantities, and flux is equal to BLV. Again from B2 to B here, what happens, it moves parallel, because the uh, let us see B to B. So here 0 to B we have proved, from B2 to B we have 0, again from 2B to B again 0, and again from B to x is equal to 0, there is some work done. So from B2 to B and 2B to B it is 0, so it is parallel. So no work is done here, no work is done, just parallel. Again from B to 0, there's a work, we have a value for work, force, energy, mm, EMF, everything, flux, everything. The force required to keep the arm PQ, the expression is given here. The force required to keep the arm PQ constant motion is ILB. Its direction is towards left in the magnitude F is equal to B square L square V upon R, where X is greater than equal to 0 and less than B, which is equal to 0. For this value, F is this, and for this value from B2 to B, the value is 0 because the field is 0. Magnetic field is 0. The Joule heating loss is Pj is equal to I square R. Put the value of I square here and multiply by R. And again, for this value from 0 to V, we have 0 to B, we have a value, but from B2 to B, we won't have any value. It is 0. One obtains similar expression for toward motion from x is equal to 2b to x is equal to 0. One can appreciate the whole process by examining the sketch of various quantities displayed in figure 6.12b. So here the figures are drawn, and here all the power, work done, force, etc. written. So let us leave our class till here itself, and let us recapitulate what we have done today. Today we started with 6.7 energy consideration, a quantitative study. So here what we have done, we have find the value of I is equal to EMF upon R, and put the value of EMF BLV upon R. We have done detailed y I is equal to E by R, etc. So F is equal to ILB, that is B square L square V upon R, and we found the expression for power and in one way, and also power in terms of work done, and power in terms of joules heating. So in both the cases we found the powers equation is same, that which proves the law of conservation of energy. So after that we have also find that the equation for the charge, a relation between the charge, a resistance, and magnetic flux, change in magnetic flux. Then we have seen an example 6.8 in details how the things are solved, and use the concepts in practical to solve this example. And that's it for today. In the next class we'll study 6.8 AD currents, which is a very interesting topic. Please be there for the next class. Before we end our today's session, I request you to subscribe our channel if you have not done yet. Please like and share our YouTube videos among your friends and relatives so that they can get benefited, and please click on the bell icon so that you can get automatic notification whenever a new video is uploaded by us. Thank you very much for watching our videos and supporting us. Thank you very much.